Okay, many moonshots. So quantum technology has long lived in the realm of theory and lab experiments. But today, breakthroughs are moving to the real world, and the challenge is no longer just the science, it's commercialization. In this next session, we'll explore what it really takes to translate cutting-edge quantum research into scalable businesses, which industries are primed for disruption, what policies, partnerships, and capital are needed to bring quantum from the lab to the market. To help us unpack the path from innovation to impact, please welcome, in conversation with reporter Emil Protalinski, founder and CEO at Xanadu and CD Alumni Company, Christian Weedbrook, and product manager at Photonic Inc., Kristine Boone.
Hello, Elevate. Who's excited to talk about and learn about quantum computing? Okay, I need a little bit more. It's quantum computing, guys. Come on. Thank you. So quantum computing is interesting. I feel like it's similar to nuclear fusion in the sense that every time I learn about it, it's always 5 years out, 10 years out. It's just never ending. And yet, there have been some sizable headlines lately. Every few weeks, there's a new business use case that some company is implementing with one of the many quantum computing startups. And just yesterday, there was a trio of researchers won a Nobel Prize for physics for their quantum computing work. So things are constantly happening. Today, you'll be learning about commercialization, error correction, and sovereign data. But that's enough for me. Let's hear from my esteemed panelists to my right. Why don't you introduce yourselves and tell us what you do in one sentence, starting with you, Kristine.
Hi, I'm Kristine Boone. I'm a product manager at Photonic, and we're building a quantum computer that can both act as a quantum computer as well as a quantum network.
Hey, my name is Christian Weedbrook. I'm founder and CEO at Xanadu, and we're building photonic quantum computers. We're a full stack company, meaning we work on the hardware, building the quantum computers themselves, as well as the software. We have world famous, I think you were saying world famous, Penny Lane software, and we also work on the business use cases as well.
Awesome. So there are many ways to build a quantum computer. Unlike a traditional computer, we've kind of settled on how a bit is made. It's a transistor, it's an on and off switch. A qubit, it's not so simple. And by that I mean there's different technologies that one can use to build a qubit. So why don't you kind of spell out how your companies, it might seem like you're doing the same thing, but turns out you're not. So just kind of give us an overview of how your specific company is tackling the problem.
Perfect. Yeah, don't let the name of our company deceive you. We're not actually building a photonic quantum computer, even though the name is...
That irritates me so much.
Oh, you and me both. But the idea is that it's a silicon spin qubit, so that won't mean a ton, but has telecom interconnect, so that's where the photonic name comes from. But yeah, generally the idea is that it can act as a quantum memory. So the fundamentals of what you need to build a quantum computer come down to you need to be able to store information while you're running a long computation. You need to have low error rate. So the idea is that quantum computers are like intrinsically very noisy and error prone, and errors like to spread all over the system in these crazy ways. But you need to be able to reduce your error rate, and we'll talk about error correction in a little bit here. But you also need to have low cost. And the big thing that we'll probably end up talking about today is you need to be able to scale. So our system is designed so that it's on silicon chips, so it's easy to manufacture, but also we can both scale by putting a ton of qubits on a chip, but then we can also, because of the natural way that it emits these telecom wavelength photons, we can connect a bunch of chips together as well. So. But yeah, it comes down to solving all these different problems and finding a qubit that can do all these things. So again, there are a bunch of different qubits out there. There's a bunch of strengths and weaknesses for all of them, right? And the technologies are so fundamentally different that the lab equipment at Xanadu, there's probably only like, maybe not even a handful of things that would be in our lab. Like when we talk about a regular computer, at the base of a lot of them, they're all pretty similar, right? Almost the same. Whereas for these different kinds of qubits, they're completely manufactured differently, and they couldn't be more different than they are. So.
And the technology that you're using for your qubit is?
Silicon spins so they're called T-centers, but they're, yeah,
Okay.
T-centers.
And Christian?
Well, we're called Xanadu. Originally, was going to be called Spin, but then we thought we better not. But we use photons to encode information. Really, you can you can build a quantum computer out of anything as long as you can access its quantum properties. So we're using photons. So I think laser systems, beam splitters, phase shifters, and things of that nature. And a lot of similar things where we can use advanced manufacturing like foundries to build our chips. And ours has 3 different types of chips within the computer itself, and it's networked using fiber optics as well. But the fun aspect is really from end to end, you have photons kind of running around the quantum computer, and you're using that to process information.
Okay, so in sum, quantum computing is very complicated, but just to make it a little more complicated, Photonics Inc., not using photons, spin.
Well,
Xanadu.
the qubits are not, the main qubits are not the photonic qubits.
Right.
Yeah. It is not a photonic quantum computer.
And Xanadu using photons.
That's right, yeah.
Okay.
Yeah. You can call us both photonic.
Yeah. Perfect.
Yeah, I mean, let's not break any news about merging here. So the title of this talk is Commercializing the Qubit. Now, most quantum computing startups, if not all of them, would say that they are already commercializing quantum computing. They're doing it. So I don't think we're going to break any ground there. However, my understanding is it really comes down to this: how much can you scale? How well you can commercialize quantum computing ultimately comes down to, like you were saying, Kristine, earlier, it comes down to scale. How many qubits can you scale up with? And we'll talk about error correction in a bit. So I'm curious, am I characterizing that correctly? Does it all just come down, is that the main obstacles, can you scale? Starting with you, Kristine?
It comes down to a bunch of things that I just mentioned, right? Like you do need a ton of qubits, right? So you need to be able to scale your number of qubits however you want to scale those. But you also need to make sure that your error rate is really low. You don't want to spend a ton of money trying to use a quantum computer to solve some big problem and then not get the right answer out, right? You also need to have low costs, right? You need to be able to have qubits that aren't extremely expensive to add more, right? You're going to need like hundreds of thousands or millions of these qubits. They can't be super expensive to build and maintain. You do need a bunch of qubits, but it does come down to like a lot of other things, as well as like rate, like how quickly can the quantum computer run? You can't have it run forever, right? It needs to be able to do computations fast enough, but also fast enough so that your system doesn't decohere by the time that you're done the computation. You don't want to have the wrong answer at the end because it took so long to run.
Okay, so speed, error correction, scale.
Cost.
Anything missing there?
No, I think that was great. I couldn't have said it better myself.
Okay, fair. So speaking of error correction, can you kind of explain to the audience why is that so important in quantum computing?
I'll let you start one, I feel like.
Yeah, with any sort of substrate, however you build, well, any device, as mentioned, you want to make sure that whatever you do gives you the right answer. And in classical or sort of our chips and phones and computers, I think it's something like an error does occur on those chips, but once every billion years or something crazy. And that's taken like decades to get to that point. Quantum computers are much newer, but it's also, you have to deal with our world. So our world kind of interferes with the world of quantum. So if you zoom in on some object, you get down to the atoms, the electrons, and so forth. And it's a very different world governed by different laws of physics, quantum physics in that case. So what that means is when you're trying to compute at that level, our world is infringing upon it. And what that means is it's going to cause errors. In our case specifically, because we have photons throughout the computer, not all the photons make it from start to finish, and that process is called loss. And so whenever there's loss, it induces the effect of an error. And so if you have too many errors, you're not going to get the right answer. So that's not a good thing. So what you like to do is have redundancy in the system. Very much like error correction occurs in telecommunication and Wi-Fi and long-distance communication. You have to correct things because as they go across, loss picks up and accumulates. So what we do in quantum computing for all modalities is you need to have some form of correction, and that's called quantum error correction. And at one point, it was probably in the 90s now, people thought that maybe you couldn't scale up and build a quantum computer because they hadn't invented error correction and the quantum version of error correction. So that was one of the big discoveries, probably worthy of a Nobel Prize one day as well, once we can really show the full use of error correction on a large-scale quantum computer. So yeah, that's why you need error correction.
Yeah, and I think just to like conceptualize what we're talking about with how these quantum systems are so different than anything that you guys can think of is like the coldest place in the universe is on Earth because we need to, for many systems, not all, room temperature, but for many systems, it needs to be pretty much absolute zero, right? Like our environment affects the quantum level so much that it needs to be pretty much no stray electrons are floating around, right? Like, yeah, so it's not like in a regular computer that has so few errors. It's a problem, and it is something that, like, as a academic community and as an industry, we've been working 20 years to resolve it, right? We see these huge developments in people getting their error rates really low, and there is a threshold. There's a threshold that you have to have a low enough error rate on each of your qubits, or these basic building blocks, in order to use these error correction methods. And so, it's interesting because there's a bunch of different ways of doing error correction, and kind of as time goes on, there's more and more options. And right now, if you have the ability to connect any qubit in your system to any other qubit in your system, it unlocks the ability to use, it's called quantum LDPC, but it unlocks this really efficient method for error correction. And so you don't need nearly as many qubits to represent one really good qubit. You can use way fewer, which is really, it's a huge advancement in the community. And it's nice because with our system, we do have this ability with this telecom emission to actually connect any of these qubits. So we were able to unlock this LDPC recently.
Is that where you think things are heading, is just better and better versions of error correction?
For sure. There's a whole community of people working on how do we make this more efficient, right? Like you can't, a lot of different error correction methods can use hundreds or thousands of physical qubits, like the noisy, messy ones, to represent like one really good one. And so as we can get that number lower, we'll just need smaller systems to do the same thing. So the theory work and the experimental work are both equally important in order for us to bring like a full scale system to the market and be able to solve these really interesting problems.
Is there a world where error correction no longer is required? Christian, what do you think?
Well, in the extreme, there's no error correction needed if everything is working perfectly. Whenever you see these textbook algorithms, you just see these lines and boxes and stuff that show the quantum circuit. They're assuming everything works as advertised. But I don't see, I don't see a world where things become that perfect where you don't need any. Hopefully, you'll have a reduction in resources that are needed, like LDPC codes are a great example of that. But it'd be hard to see that you would never need it. Just our world is just chaotic and noisy anyway, so it's hard to see it eliminating it for 100%.
Yeah, and yeah, the error rate that you would need for running like really big algorithms like Shor is like 1,000,000 times lower error rate than what we're currently at, and you would need like 1,000 times more qubits. It's just, I can't imagine a world where that's possible, but again, like we're making huge strides every day as a community, so yeah. In theory, it could be possible, but I don't think it probably will in practice.
That's fair. Okay, so we've talked about commercialization, we've talked about error correction. Our last topic is sovereign data. I work with a lot of AI companies, as you imagine. Everyone's talking about AI, and a big theme there is sovereign AI. And I believe something similar is happening in quantum computing. So I'm curious, what does sovereign data mean to your company? Again, let's start with you, Christian.
Well, I mean, we're hearing about all the challenges we have as Canada with the tariffs from the US. I think that's, it's tough at the moment. I think in long term it'll work out. But one of the benefits of this that benefits, to Canadian companies here is the fact that it is pushing, us, but mostly the government to think more sovereign in terms of the data, in terms of the technology, in terms of the supply chains as well. And that's very beneficial. We're hearing through public statements by ministers and their intention to push a lot more capital into quantum computing for companies such as ours. So that's really exciting and has many positive effects as well. But in terms of the data, you often hear it about it in terms of artificial intelligence and the needing of a lot of data, protecting it. That will be true for quantum at some point, but there's other things to kind of worry about at this moment. The algorithms that quantum computing in general can work on are related to drug discovery, material design, batteries. We work on next generation battery development. So all of those things, you can imagine having our quantum computers located in Canada, but also sell the sort of small set of server racks to other companies to have in their countries to solve sort of the data problem as well. So I don't see it as a big issue. I think the biggest thing we all need to keep our eye on is just trying to get to a large scale quantum computer and then kind of going from there.
Yeah, and I think also, like, this is not, well, it actually has kind of started today, but globally there's been starting to have this conversation of what policies will be in place for how quantum computers can be used globally, right? And so as a country, it would be great if there was at least 1 or 2 quantum computing companies that were at the point of this commercial scalability when that conversation's happening, so that Canada can actually really have a voice in the room when we're talking about how these quantum computers will be used, right? There's a bunch of benefits to using these quantum computers. There's also some concerns with cryptography, right? And so we want to make sure that we're positioning Canada in a way that can be part of this discussion as we kind of move forward and how we're going to use this as a society.
So we're getting close to time. I want to just get a few questions out. Kristine, you mentioned a few sectors that, as you were talking, if you could pick just one sector that you're particularly excited about where quantum computing you think will make a significant difference.
Yeah, we work on quantum chemistry and material design along with other companies, and we focus a lot of the work working on next generation batteries. So how do you create a new battery that could be 10 times faster to charge, perhaps 10 times longer distance, range, and all that sort of stuff. But a lot of this stuff the skills and breakthroughs gets transferable to other things in material design when you're developing new candidates. And also because we're running out of time, I would say this is such a great opportunity, like with what our companies are doing, to really create the focal point of quantum technologies around Canada. We have a great opportunity to build something truly great in Canada. I was a postdoc at University of Toronto, and we have about 250 folks now. Half are from Canada, and so the government's put a lot of time and money into educating. We don't want this brain drain of all the talent that's happened in other industries. So, apart from the use cases, we're really excited to build something great here in Canada as well.
Yeah, and just to echo that, like, Canada invested very early into quantum and has been a leader in quantum from like day one. And so I think the other countries are now having very aggressive approaches to kind of catching up or pushing their industry forward. And I think that it's really important as a country that we continue to invest and support the quantum computing industry as a whole, right? Like, we're trying to build something that might be the most difficult thing that humans have ever tried to build, and we need the support of a nation to do that, right? And I think that as a country, if we could actually support that community, but then also position ourselves on the global stage with that technology, I think.
And Kristine, what one sector that you're pretty excited about?
Same as material design and pharmaceuticals. I think that would be really cool if we can use a quantum computer to discover very unique chemical structures that could be used for the pharmaceutical industry.
Okay, final question, because we're really at time. We started talking about qubits and how there's different ways of designing one. Let's say the way that your company is doing it disappears or becomes no longer relevant because a different technology has clearly won. We finally figured out what a qubit should be. So quick one-word answer, what is that technology in your opinion? Kristine?
Oh, if it's not ours, honestly, probably photonic systems.
Okay, and Kristine?
I have to reciprocate.
Wow, look at this, look at this. All right, I mean, you're both Canadian, so you're very polite. Thank you so much.
Yeah, thank you.